which is talking about the scientific method. So, situation is the laws are just some kind of pattern. That's it. It's a pattern. But some people say, why does that pattern exist? Or, is there something more fundamental as far as an explanation for that pattern goes? And so that's where the things come in. For example, why does the pen fall? Why does it fall this way? Why doesn't it fall sideways? Why doesn't it fall up? There's lots of questions there. And so to dig deeper into it, then people come up with a hypothesis. And what a hypothesis is it's a fundamental description. It's a fundamental digging at a very deep level, or as deep as you possibly can, a level as to explain. This pen falls. Yes, we can observe that. That's a law. The pen's always going to fall down. It's never going to fall up. Right? If somebody observes the pen falling up, then we've got to kill that law because it's a violation of the law. Laws aren't supposed to be violated like that. And so a hypothesis, this is a tentative, fundamental explanation of the phenomena or the law or the observations. And so it's trying to explain this at a deeper level. So one of the hypotheses for this law, the Newton's laws, like for example, is gravity. There were probably other hypotheses too, but this is the one that lasted. Because eventually what happens is this tentative fundamental explanation, this is where this stuff comes in. Obviously there's going to be skeptics. What is this gravity? I don't believe in this invisible force called gravity, right? Whatever it is. What is attraction between? And so that's where the skepticism comes in. And so that comes with testing. You test it. And so somebody's going to be testing. They're going to wait for the pen to fall up. And then see, it's wrong. This whole idea or notion of gravity. It's like there's another set of laws dealing with energy. It's called the laws of thermodynamics. And people have been trying to violate the laws because if they could violate the laws, they could become very rich. Because if you can develop something that violates the laws of thermodynamics, like for example, a perpetual motion machine. Have you ever heard of a perpetual motion machine? Then you'd be very rich. You don't have to put any energy; it just keeps going. This kind of stuff, perpetual motion. But no one the laws of thermodynamics have been around since the late 1800s, I think, or sometime in the 1800s they were developed. And people have been trying to violate the laws of thermodynamics since then, but nobody has ever found a violation of the laws of thermodynamics. Nobody. Well, anyway, getting back to this, obviously you're going to have skeptics, and that's a great thing about science, because science is like this. Science is a self-policing kind of organization because you're always going to have skeptics, and this takes some getting used to. If you don't have a lot of science tests, as you progress in scientists, the degree of skepticism can become pretty severe. So, when you're at the university, for example, some of the professors, you're going, wow, they're really harsh, because they're attacking your ideas or attacking left and right. But that's the nature of science. The nature of science is you got to attack people's ideas to filter out the junk science, and then the good science can filter through. And so this self-policing thing is called, peer review. You have your peers, essentially try to find holes in whatever hypothesis or whatever thing you're proposing. And so that's going to happen. And there can be competing hypotheses. Exactly. There must have been competing hypotheses in this situation too. But once you've convinced all the skeptics that, and you convince them by doing this testing, doing this, and coming up with a sound fundamental explanation, then the hypothesis turns into a theory. A hypothesis turns into theory. This is an accepted or generally accepted. It's hard to convince all the skeptics, and some skeptics will just not listen to whatever. But this has general acceptance, so it's an accepted fundamental explanation. And so a hypothesis is a tentative fundamental explanation. A theory is an accepted fundamental explanation. So here's where we come up with a theory. So, for example, Newton's, the apple falling from the tree. The hypothesis is the force of gravity pulling two masses together, the apple and the earth. Right? Okay, then based on that theory, you can derive equations, mathematical equations, and from that we can actually go backwards here. Rather than coming up with an empirical equation, we can come up with an equation that comes from the theory. What is the mass of the earth? What is the mass of the apple? What's the force pulling them together? That's the force of gravity. And so based on those, the theoretical here, we can work backwards and derive all the equations that we got empirically. And so those are equations based on theory versus equations based on observation. That's the distinction here. This is why we call this empirical. We have other names where we get equations from theory. It depends on how much, because there are hybrid equations. And so we have empirical equations, and we have things called ab initio, which I'm not even going to bother writing. Ab initio equations that come from theory. And then we have equations which are hybrid, because sometimes the theoretical equations are a bit too much, so we have semi-empirical equations. Semi-empirical equations take a little bit from the theory and then mix that with the observation, empirical equations, and come up with a more manageable equation than these types of things. But anyway, obviously the theory's got to predict the law, that at least, it's got to describe this law. But theory's got to do one more thing. And that is, a theory must make new, unforeseen predictions. And so, accepted fundamental explanation plus it must be able to predict, unforeseen observations. And so the theory, we should be able to apply the theory to other systems. So for example, on the moon, figure out the mass of the moon, mass of the apple, and figure out how fast that apple is going to fall to the distance of 3 feet. That's what a theory would do. And so and then we go test that theory. Somebody takes an apple to the moon, drops it, has a stopwatch, times it, boom. Did it predict it or did it not predict it? If it didn't predict it, then there's a problem with the theory. Got to go back. Revise the theory, that kind of thing. Does that make sense? Well, the theory did predict it. So this is the scientific method. A lot of people say, well, you got to come up with a hypothesis. Coming up with a hypothesis first. Can you hypothesize gravity? There's some force of gravity. This is too hard to hypothesize, right? So science starts with observation, so it's a very simple process in that sense, because we're just observing things like pet behavior. Can you predict pet behavior? It's kind of complex. You got to take a lot of observations, got to figure things out, right? The same thing with science. So let's look at some of the book's features of the scientific method: observing, right? Observation, that's what scientists do. And then they skip some steps. For me, they skip some steps. They come up straight to proposing a hypothesis. Okay, let me give you an example of that. I don't like this skipping a step, because if we go back to this chart, okay, here are my observations, give me the hypothesis, give me the fundamental, deep description of what's happening from my observations here. So I got a whole bunch of observations here, maybe 1,000 observations or something. This is a small subset of those observations. Can you come up with a deep fundamental hypothesis of what's going on here? No. And so skipping those steps is too much. I think that's too big of a jump right there, because to come up with a hypothesis, now that's going to take some genius there. I can't do that. So I don't like the way it's presented in the book, because it makes science just orders of magnitude more difficult than it should be. To come up with a hypothesis. To come up with a hypothesis here at this point is too much. Too much. Instead, what do? We look for patterns, and from those simple patterns, then we can make some generalizations, maybe a law. And then we can better understand things. This would be like the seconds, you know? Like say the seconds it takes an apple to drop, except ignore the negative ones. If you look at the seconds, can you come up with a deep hypothesis by looking at how many seconds it takes to drop from different heights? All of a sudden you're going to come up with gravity. Oh, shoot. Wrong button. Well, scientists by nature are skeptical. Predicting an outcome that should result if the hypothesis is true. Obviously, we want to test the hypothesis, and people are going to test the hypothesis no matter what, because they're going to look for holes in your hypothesis. Testing the prediction by an experiment. We test quantitatively. Quantitatively means try to take accurate readings. Obviously, if the hypothesis has some failings, we revise it. Testing the revised or new hypothesis and predicting a new experimental outcome, upgrading a hypothesis to a theory. Okay, the theory is the ultimate aim, because what we can do with a theory, if you know the theory, then you don't have to really do any memorization because you can predict things theoretically. And so if you know the theory, then we can predict lots of things without actually having to observe them. And that's the power of the theory. This is why people want a theory. They want a good theory. And so this is why we say upgrading hypothesis to a theory. And theories, obviously, they have to be confirmed. You know, if there are violations of the theory, then that's a problem. And so there are lots of examples of the scientific method in science, history of science, etc. All right, the scientific method, let's continue with the slides. Communication has led to the growth of scientific knowledge. Modern scientists communicate with each other through technical knowledge. Well, yeah, that's it. Then they come up with this law. The law is a summary of a pattern or of regularity detected in nature. In order to be classified, the law must have no exceptions. Laws shouldn't have exceptions. Otherwise, like the laws of thermodynamics, they don't have exceptions. Now, there are some laws that might have some exceptions. But those exceptions are well understood. And so the law is known to have certain limitations, and those limitations are well described. But this is kind of out of place for me. I mean, these slides aren't exactly, and the book, I assume, is organized in exactly the same way, so it's a little different than mine. Now, what should you emphasize? Should you emphasize the way the book does it, or should you emphasize the way I do it? You should emphasize the way I do it, even if the way I do it is more confusing, or it seems more wrong, or it seems whatever. What you want to do is you want to learn, especially for exams and testing. I'm going to be writing the exams. I'm going to be grading the exams, and so what's most important is what I present in class, not what the book presents. Okay, and so if I deviate, then make sure you follow the way I do it. Not the other way. And it doesn't matter. A lot of you are biology majors. I know that. In biology, they also teach the scientific method. The scientific method in biology always begins with a hypothesis, right? And testing the hypothesis. But I don't want you to write that. I know you've learned that in biology, but I want you to write it the way I wrote it, right? In chemistry. And so, well, chemistry today, chemists, what do they study? They don't study molecules. Because not everything's made up of molecules. We'll talk about that later, some things are just made up of atoms. Some things are made up of molecules. Some things are made up of structures, which we'll talk about later as well. But anyway, chemists study matter and its changes from one substance to another. In other words, matter is the physical material of the universe. That's what we call matter. And so the chemists are interested in how the world works. Okay, energy is important. Energy is not really physical material of the universe, but chemists study energy because in certain changes, like when you burn things, energy is consumed or energy is released. And so we're very interested in that. chemistry today holds a central position in science. I mean, it kind of studies the physical material of the universe. You know, physicists also study the physical material of the universe. Biologists study the physical material of the universe. Geologists study. All these sciences study matter. You know, just certain types of matter. That's what they're interested in. You know, biologists study living things. Say geologists study minerals, rocks, and stuff. That's all made up of matter. So chemists study matter in general, so they're interested in all these things: physics, biology, biological, and geological systems. Okay. Industries employ chemists for research and product development, whether it's catalysts or drugs or whatever. Quality control, product supervision, sales. These are some of the jobs chemists do. It's not limited to that. There are many jobs. There's just a graphic showing chemistry. Obviously, chemists study matter, and it's going to touch on all the sciences here. So what we want to do is we want to understand now, although chemists study matter, we subdivide it because there's lots of different types of matter out there. And so biochemists will concentrate on living systems, on the matter that's involved in living systems. Organic chemists, they study matter that contains carbon. Carbon, the chemistry of carbon is very rich because the way carbon can attach to other, what do we say? You guys know about the elements, right? The other elements. We'll talk more about it. Inorganic, they study substances that are not organic, that aren't these carbon-based. There are some carbon-based substances that are considered inorganic, like carbon dioxide. Carbon dioxide is considered inorganic versus organic, even though it does contain carbon. Whereas methane, which contains carbon as well, is considered organic. Physics is, if you're interested in physics, there's physical chemistry, which examines the border between physics and chemistry. And analytical chemists are interested in what type of matter, how much of it, and so different types of chemistry. And then there's lots more. You know, this is a limited list because you have the physical chemists and you have the chemical physicists. What's the difference? You have the biochemists and you have the chemical biologists. And then you have the molecular biologists, and then you have the geochemists and the chemical geologists. You have all these depending on what their emphasis is. But really, when you study matter, the matter behaves similarly, whether it's a biological system or inorganic system. You know, the carbon atoms behave like carbon atoms. You know, all of a sudden, if you have carbon atoms in the biological system versus carbon atoms in the inorganic system, you know, it's not like there's a big change in the properties. It's like, you know, if you have a Doberman here and a Doberman in another state, maybe some traits are going to be the same. You know, that kind of thing. All right, so learning, what you should think about is you need to commit. You know, learning chemistry, you got a lot of memorization to do. And the reading is very slow. And so you got to make sure that you commit a certain amount of time outside of class to study. You know, normally what I do is I like to have the time after class free. I know some of you probably have a class right after this, which makes it complicated to study because the reason I like to have time outside of class is because I'm a slow writer also. So there are some things that I don't have enough time to write down, but I remember. And if you remember it, then after class you can write it down to complete your notes and stuff. And so make sure you have enough time. I'll talk more about this actually today, later today, or tomorrow. All right, some other tips. So you can take these tips or leave them. But the most important is make sure you have enough time to study. When chemists think about things, you know, they visualize things with different different ways. We visualize like water. Visualize that looks like boiling water there. And sometimes we visualize water by what makes up the water. What makes up the water? Hydrogen and oxygen make up the water. H2O. And how is that H2O structured? Structured like this. This is a molecule of water here. So a sample of water like this has lots of these little particles. You can't see them because they're so small. Here we're just writing the process here. We're just taking water in the liquid state and then boiling it to water in the gaseous state. So we'll have water molecules here that are boiled off of steam. So different ways of thinking about things. And so as far as chemists go, we do all this. And we have a multi-pronged approach because what we want to do is we want to make predictions. We don't want to have to memorize everything, right? And so we take a multi-pronged approach because ultimately we're interested in the properties of matter. Properties. And properties are how things behave, or how things work. For example, an automobile. The properties of an automobile are going to depend on what? The properties of an automobile are going to depend on, what is it composed of? The composition. Is the automobile built out of aluminum or is it built out of lead? Not that there would be any lead, maybe in the old days, or steel, that kind of thing. And then, we'd also need to know the structure. It's made out of steel and a bunch of other stuff. Well, how's it structured? Okay, that will give us an indication of the property. Now, this composition structure properties, we have like a two-pronged approach to this. On the one side, we take observations, we observe things and see how they behave. On the other side, we have theory. If we have a good understanding of theory, we can make these predictions. We can make predictions about how things behave. And so we use both observation and theory to help us understand this. And so what we'll want to do is we're going to do some memorization to see these patterns. And once we learn the patterns, sometimes the theory is not well developed, sometimes the theory is complex and confusing. Other times the theory is not so complicated. Ultimately, we'd like to know the theory, but sometimes it's a little too hard, so we just go by with patterns from the observation. And from there, we can make predictions about this type of stuff. Okay, when we look at our textbook is going to have goals. I'll talk about these goals. We'll see in the next PowerPoint. And then these learn it now sections, and then what they call active examples, this worked out problems, target checks, reviews, thinking about your thinking, etc. And so there's some resources that you can find in the textbook. Let's move on to chapter 2. All right, chemists are interested in matter and energy. What's the difference between matter and energy? Well, matter is the physical material of the universe. When we think about the physical material, like this table, this is physical material. This faucet's physical material. How about the air that we breathe? Is the air that we breathe physical material? And one way of defining physical material is that it occupies space and has mass. So the air in this room, it seems to occupy space, but does the air in this room have mass? You know what mass is? It has weight. And that's what mass is. And it does. I mean, if you do this, can you feel you pushing the air molecules, air particles, back and forth? Yeah. Or if you ride a bicycle, or if you stick your hand out the window when you're driving, you can feel the air. So that has mass. Well, this room could also be filled with a vacuum. Do you know what a vacuum is?
It's when there's nothing there.
Yeah, so when nothing's there, and so there's no matter in there. It's empty space. Well, the room in here is not a vacuum. Because if it were a vacuum, we wouldn't survive for very long. For sure. Now, energy, like the energy coming from the light here, we see the light. Is light matter? Now, light we don't consider matter because it's missing the mass part of it. Light we consider as energy, although we should say rest mass. Light is a bit tricky, and also with the new developments in particle physics, there's a little less boundary between matter and energy. Have you heard of like this super collider in Europe? Have you heard of the Higgs boson? Okay, there's a little bit less. They're a little bit more connected. Okay. But anyway, those are the differences. Chemists obviously are interested because light is going to impact matter. So, for example, what color is this? Blue. But if I turn off the lights, is it still blue? Is it still blue if I turn off the lights? Will we ever know? I don't know. Yeah, you know what? It's not blue, right? If there's no light, it's because it's how the white light interacts. If I shine black light on it, is it still blue? No, so obviously chemists are interested in how light energy interacts with matter. If I shine X-rays on this and no visible light, is it still blue? No. And so, and the same thing with leaves or whatever, photosynthesis. We're interested in the effect of energy and matter. And sometimes, matter releases energy and consumes energy in certain changes. All right, these are what I was talking about earlier, the learning objectives. So this is a breakdown section by section of the chapter with learning objectives. So in section 2.1, the learning objective is to identify and explain the differences between interpreting, describing matter at the macroscopic, microscopic, and particulate level. Define the term model as it's used in chemistry to represent pieces of matter too small to see. Section 2.2, identify and explain the differences among gases, liquids, and solids in terms of A, macroscopic level properties, shape and volume, particle movement, and C, particle spacing. 2.3, distinguish between physical and chemical properties at both particulate level and the microscopic level. This is where we define it. If you recall, what was the dictionary definition of chemistry?
Composition, structure, properties, and reactions of the substance.
Yeah, and reactions of substance. And so when they're saying properties, let me just go back to this really quick. This is what I didn't like about the dictionary definition. I didn't tell you, but I'll tell you right now. What I didn't like about the dictionary definition is this. To a chemist, there are two types of properties. For a chemist, the two types of properties are physical properties. Physical properties would be like hardness, what is it on the Mohs hardness scale? 0 to 10. Can you go over 10? Is there anything harder than diamond? Is there anything harder than diamond? Is 10 the max? No, it's not. 10's not the max. There's harder than diamond. So there's things that are like 11. I forgot what the peak, but chemists are trying to develop even harder materials. That's one of the goals, because if they understand matter, then they can design it. Try to design things that are harder than diamond. But anyway, we got physical properties like boiling point, melting point, volatility, etc. Then we have chemical properties. Chemical properties are reactions. And so to chemists, we eliminate this and reactions, and then we just talk about physical and chemical properties. Oops. So that's correction. All right. Distinguish between a pure substance and a mixture of both the particulate level and the macroscopic level. Distinguish between homogeneous and heterogeneous matter. Describe how distillation and filtration rely on physical changes in properties to separate components and mixtures. Distinguish between elements and compounds. Distinguish between elemental symbols and the formulas of chemical compounds. Distinguish between atoms and molecules. State the law of definite or constant composition and explain its implication for how compounds and mixtures differ in composition. Match electrostatic forces of attraction and repulsion with combinations of positive and negative charges. Chapter 2 is getting a lot longer here. Distinguish between reactants and products in the chemical equation. Distinguish between exothermic and endothermic changes. Distinguish between kinetic energy and potential energy. State the meaning of or draw conclusions based on the law of conservation of mass. State the meaning of or draw conclusions based on the law of conservation of energy. And the law of conservation of mass and energy, which is one that's not here. There's a lot of learning objectives in chapter 2. But let's go ahead and jump into chapter 2. But before we do that, in a nutshell, what was chapter 1 about? And so this is why I like to have time, after class. After class, what I think about is this. I think about, okay, what's the take-home message of today's lecture? What should I write down? So you think about it. Well, from chapter 1, what was the take-home message from chapter 1? The scientific method. And can you tell me the steps of the scientific method?
Observations, patterns, law, hypothesis, theory.
Good. Can you give me an example of the scientific method in practice? Yeah, the apple falling from the tree, leading to a pattern, leading to equations. Those equations we call Newton's laws. And one of those led to, he had multiple laws, but one of those led to the theory of gravity. Yeah, so there's, chemists obviously they study matter. And so when we observe matter, we can observe it at different levels. And so when we're looking at matter is everything that makes up the universe. Basically, it's everything that has mass. And so at the macroscopic, the difference is macroscopic means we can observe it with our eyes. And so when we're looking at water, we could observe water with our eyes. But if we were to observe, can you observe a single molecule of water that is this H2O? No. That's going to be at the particulate level. At the particulate level, it's too small to be observable by the human eye or microscope. So we have something in between this, which is called microscopic. Microscopic, we can observe it with a optical microscope. It's called a classical microscope. So cells, if you're looking at the cell of an onion, I remember doing this in 7th grade, looking at cells of onion. You'd stain it, look at the individual cells, but you can't see the individual cells with your naked eye, so that would be microscopic. And then if you were to look inside the cells would have molecules inside there, but those you wouldn't be able to see with a microscope. Those you'd need something more powerful to see with. And so it says here it needs to be modeled. It doesn't always need to be modeled. You can visualize these things with certain sophisticated instruments too. Model just means you just describe it using drawings on it. Okay, this one. So I would add one thing here, needs to be modeled or sophisticated instruments are required to visualize these things. So, for example, you could see individual water molecules. If you freeze this down and get a crystal of ice, and you put the crystal of ice in what's called an X-ray diffractometer and shine X-rays at it, the X-rays will result in a pattern, and the pattern can be refocused into an image, and that image would be called the structure of water. You know? And the structure of water, there are other ways to get the structure of water too, but it doesn't always have to be modeled. In fact, we can show you. This for sure.
$1,500 attendance fee.
I'm sorry, what's that?
Sorry, news article.
Can you repeat it? I missed it.
There's a news article.
Oh, news articles? Oh, I missed it. Yeah, I wasn't paying attention to
Could be.
that. So what you could do is you could freeze some ice down and generate a crystal. And with this crystal of ice, you shine X-rays at this, and it generates a pattern. People are looking for a lens. If you had a lens that could focus X-rays, then you could actually see the molecules. You know? But what you do instead of the lens is you use a computer to rebuild the image, and this is the image that results. You know, this is ice here, and these are the water molecules. The water molecules are modeled, however, they don't look like this. This is called a ball and stick model. The water molecules are going to be much more like this. Let's see if I have a space filling structure of ice. This is one from Stanford, it looks like. Sometimes they do this ball and stick, so it's easier to visualize. Other times they won't, you know. Other times it's like this, more like this, where you see things. This is just sticks here, sticks and ribbons. You know, there's so many connections, so they just model it with how they're interconnected. This is a gigantic molecule. This is a biomolecule. But a lot of these, this top one is actual XRD here. You know, the X-rays scatter off these. These are called atoms here. These, do you look at the shape of that? Do you see it's kind of oblong? When you look at these, if you look at these balls here are atoms. The atoms are the smallest piece of elements. So these are carbon atoms here. Some carbon, you've got some nitrogen, these are nitrogen. These are oxygen atoms here. These white ones are hydrogen. This is a molecule all put together like this. And you look at these atoms are round. However, these atoms are not round. These atoms are kind of oval in shape. And the reason they're oval in shape is when you do XRD, you do these at room temperature, usually. At room temperature, the atoms are not frozen in space. The atoms are vibrating like this. And that little bit of vibration can be captured over this. So that's why it looks like that. And then these are ball and stick representations. They're just showing how they're linked together. You know, this is a space filling. These are all models. This is just a stick model. These are all representing the same thing. There. These are models. But this model on the top right was derived experimentally using X-rays. So we see particulate, and what we just saw was those single molecules are particulate level, so they're modeled in that way, but the original model was derived experimentally. It wasn't just a model made by an artist, it was actually a model measuring. And so here's our macroscopic world. You can see down to about, let's see, a millimeter, you know, or smaller than a millimeter. 1,000 microns maybe. So here we have a meter, decimeter, centimeter, millimeter, micron. You know how big a micron is, or micrometer? 1/1,000,000th of a meter. So 100 microns, 10 these are best observed using an optical microscope. You can't see these things, they're too small. Bacteria cell, 1 micron. And then we get even smaller. You know what's smaller than a micron is a nanometer. There's micrometer, nanometer. Nanometers, we're going to need optical microscopes. Aren't good enough. We'll need an electron microscope. This virus here, a protein. Aspirin's getting at the particulate level, you know. And so aspirin, the way the structure of the aspirin was determined was using X-rays. We put this into an X-ray, what we call X-ray diffractometer, a single crystal, and they see, you know, how the atoms are structured together. Aspirin's made up of carbon atoms, which are the gray ones, oxygen atoms, which are these red spheres, and hydrogen atoms, which are the white spheres. So aspirin is just made up of carbon, hydrogen, and oxygen. This is what we call an organic chemical. It's carbon-based. Here's water molecule. Water molecules on the order of 100. Now, it goes N stands for nano, P stands for pico. Picometer is 10 to the minus 12 meters. Nano is 10 to the minus 9. Micro is 10 to the minus 6. We'll talk about those later. And then single atoms. These types of things will need an electron microscope or scanning tunneling microscope or X-ray diffractometer to visualize these things at that level, extremely small level. And so basically the take-home message is macroscopic, you can see with your eyes. Microscopic, you need a microscope. Particulate, you need sophisticated instruments. You don't have to memorize any of these here. Okay. Then as far as the models go, see, are the clocks, I gotta make sure, are the clocks synced? No. Clocks are not synced. What time do you guys have?
104.
Alright, 105. I got 105 here, but I was going off that clock there. It's 101 on that clock, now 103. Well, we'll stop here. That's fine.